Um, Thanks for coming to the edges of New York City to hear me chat about space. So my name is Joel Green. I am an instrument scientist at the Space Telescope Science Institute in scenic Baltimore, Maryland, which is known only for being the premier place to go to see space telescopes. Has no other reputation. And those telescopes include, as you said, the Hubble Space Telescope, the very exciting James Webb Space Telescope, and the forthcoming Roman Space Telescope, which you will hear about in 2027. So keep that on your calendar. So thanks for coming. So I'm going to talk a little bit about some interesting things that have happened recently. Now, in my career for the last, I got my PhD in, oops, I got my PhD in 2008, and since really the early 2000s, we had been anticipating the launch of the James Webb Space Telescope while we were working on its predecessor, the Spitzer Space Telescope. And this was such a massive technological leap over everything that had been put up there before. And we wondered kind of, what new discoveries are going to make. What is it going to be like to have the James Webb Space Telescope? And I'll tell you that we had the inspiration already in the Hubble, and I'm going to talk a little about that story. But first, let's take you to December 25th, 2021. That's right, Christmas morning, when no one believed that the French would really want to go into work and launch a space telescope, and they did. So let's see what that was like. First video, please. And here you're going to see the final view anyone in humankind will probably ever have of the James Webb Space Telescope as it left its Earth orbit, left its Earth, the area of Earth, deployed its solar panel, and went off into the wilds. It traveled 1,000,000 miles to the second Lagrange point, which is a stable, mostly stable gravitational point, 1,000,000 miles directly away from the sun from the Earth. So if you know which way the sun is, you want to know where Webb is, it's exactly the opposite, 180 degrees away at any given time. And it orbits around that point and does all of its science from out there. It's a very special point in space which enables the Webb telescope to do its work best by being shielded from the very sun while also drawing power from it. So I want to, when you imagine, people were speculating all sorts of things that Webb could do. I want to take you back 30, well, at that point, 31 years to 1990. Next image, please, just to set the mood here. Okay, all right, does that help? Yeah. Macaulay Culkin just got his star on the Hollywood Walk of Fame just the other day. Pretty neat. So anyway, things come around. Um, in 1990 or in 89, leading up to the launch of the Hubble Space Telescope, everyone wondered well, some people at least were wondering, what the heck is this thing going to do? Why are we launching this giant telescope into space? And the next slide, I think you can see some of the media reports at the time, if I recall. Let's see. Nope. All right, the next slide is Hubble itself. So, what is Hubble? What was Hubble? Here we go. Okay, I'm going to read something to you first. The $1.5 billion telescope is expected to provide astronomers with a vastly sharper, clearer view of the most distant reaches of the universe. So, it's number one, $1.5 billion. They just want to remind you that we spent that money on it. That's like 2 fighter planes. Anyway, and it's going to discover distant universe galaxies. That's it, right? Nothing about anything else. In reality, Hubble is actually a general purpose observatory. It does all kinds of studies, one of which is the early universe. but there are many other topics, a few of which I'm going to touch on today. If we can go back to the animation of Hubble, I can show you a couple of things about Hubble itself. Great. Okay. So the Hubble Space Telescope, and this is a computer simulated view, but we have pictures of it up there. It only sits. Remember, I said Webb went 1 million miles. Hubble's only about 350 miles up. Orbits the Earth in a quick orbit that it goes around the Earth in every 97 minutes, so like an hour and a half. And it uses about the power, same amount of power as an industrial strength hairdryer. Not a lot, just enough to be powered by those solar panels. As it whizzes around the Earth, about 17,000 miles an hour, you can actually see it on occasion as a relatively quick-moving satellite across the sky. If you see something that kind of trails for a couple of minutes, it's probably either Hubble or the International Space Station, which is at about the same altitude. And Hubble stays up there, and we've serviced it 5 times. It's been upgraded between 1990 and 2009. And I, in fact, worked for one of the instruments that was installed in 2009 as a Hubble instrument scientist. My job at the Space Telescope Science Institute is to help astronomers who want to use Hubble optimize the way that they use it, because it's actually not, turns out it's a little complicated to use it properly. So we help people with a lot of advice about its funny quirks. Now, for scale, Hubble, sitting up in space here, is about the size and aspect ratio of a school bus. So it's about 50 feet long, and the mirror, which is inside the tube, protected a little bit, is 2.4 meters, which is about 8 feet across. So imagine your backyard telescope with an 8-foot size mirror. Throw it in space. That's what you got. All right, next slide, please. And then after this one. Great. So NASA launched this amazing space telescope, and we had talked about how it was going to blow everyone's mind, show different distant galaxies, and so they decided to prove to the public that it was really worth it by showing this comparison on the left of 4 stars, and on the right there are 5, slightly. So they really impressed everyone with their calibration images, and fortunately nobody paid any attention to this. It's a lot better than that. And you'll see how much they've learned when we later in the talk discuss Webb. So next slide, please. So what did Hubble really do? Well, I think the thing it did the most is it completely changed science fiction. It changed the way we view the sky in every famous film. So if you look at this image of the Millennium Falcon, you can see in the background dots. Right? Okay. And on the next slide, on the top in The Wrath of Khan, if you can get past the screaming Khan, if you look, there's like, they decided to stick the Enterprise in a little purple haze. So that's a nebula, which they probably just heard of in 1982. Contrast that with newer Star Treks, 2015 here. I think this is Star Trek Beyond or something. Anyway, I don't know, one of the J.J. Abrams ones. And you can see here, this is in a background of what looks like it's not a true image from Hubble, but it looks clearly inspired by that. It is a tumultuous region. It's full of activity. It looks exciting, and I think that was intentional, but also it colors. If you watch movies, Guardians of the Galaxy, take your pick, and you look at the backgrounds, they are undoubtedly affected greatly by true images that have been taken by astronomical instruments like Hubble in recent times. Next slide, please. Okay, so one of the things Hubble did was when it came about, one of the things Hubble has been used to do a lot recently is to look at planets around other stars, exoplanets. This is a field that this video shows did not exist prior to 1995. While it was always hypothesized that other stars had planets, and people kind of hoped they did, we had never actually seen one until 1995. This video shows how many planets are being discovered year by year. And so I think in current days we're up to about 5,000 that have been studied around other stars. They're called exoplanets. This is a field that did not exist when the Hubble telescope launched, and yet it is integral to its science mission now. So it makes you wonder what's going to happen with James Webb. All right, next slide. What do we got? Okay. Now I'm going to focus on some interesting. So I study how stars and planets are born. They're born inside clouds of gas and dust in stellar nurseries or clouds. There's one of these called the Orion Nebula inside the constellation Orion, which is right here. And this is sort of a visible light image of the area where the stars are being born. And when you zoom in, you get this pretty image. But what people at the Space Telescope Science Institute have done is rendered it in a three-dimensional way using some fantasy about how it looks in 3D to give the sense of what it might be like to fly through one of these clouds at, well past light speed. And it is a mesmerizing video, and it's all online. But it gives you the sense of that diffuse but dense gas and dust that is collecting under the influence of gravity, but battling against turbulence and waves and things that would prevent it from collapsing. And when an area of the cloud becomes cold enough, still enough that it can fall on itself by its own gravity and combine to form a star and eventually a planetary system, that's where this happens. So these happens in collections. The sun was not born alone. It was born in a cloud like this 4.6 billion years ago with a bunch of its companions nearby. And it's just kind of amazing to imagine if you rewound the clock and you flew through the solar neighborhood, you might have come through something like this. But the Orion Nebula is famous because it's one of the largest nearby regions. So this region, which is about 1,500 light years away, contains about 10,000 newly forming stars, most of which should be the sun's mass or less. One of the ways that Hubble identified these little stars is these funny tadpole-looking things. And they're little bubbles that they're blowing out by the winds. And so from the Hubble view, this is how people used to think of star and planet formation. But from the infrared, things look quite different, as you'll see with Webb. But this is what the visible light version is. Okay, I think we can skip ahead here, although this is wonderfully mesmerizing. All right. If you want to watch that on loop on your computer forever, it's on YouTube. So this is an animation. Imagine what it might be like if a bunch of this gas collects in one place and starts to collapse. You form a central protostar, the thing in the middle, which would eventually become like the sun. And then most of the material ends up snagged, spinning around the star into a sort of disk. And in that disk, which eventually clears out to make the giant planets, maybe the gas planets form in the gassier part of the disk, and the icy planets or the rocky planets form in different conditions or at different times after the gas has been depleted. But it's just a piece of that original nebula that got snagged around the star. So we and our whole planetary system are really just the crumbs left over from the formation of the sun. If you add up Jupiter, Saturn, all the planets together and their total mass, it's less than 2% of the sun. It's really just a rounding error. But with all that stuff spinning around, it causes the star in the middle to spin quite quickly. In order to not fly apart, that star will shoot very narrow beam jets of material out from both axes, the top and the bottom. We don't know exactly how that works, but those jets will penetrate through the cloud and create extremely striking structures, which we're going to see today. Okay, next slide, please. This is one of the most famous star-forming regions. It's a little bit farther away, but it is a little more massive. It's called the Pillars of Creation, artistically. It was featured on postage stamps back in the 90s. And this is actually the 2014 version, so it's a little bit higher resolution because Hubble was upgraded and takes better pictures. So this is the Hubble's view of the pillars. And this is, columns and filaments of gas and dust. And from this point of view, back toward the edge of the theater are a bunch of very massive stars that are blowing a wind this way down here and are blowing back this cloud. So these fingers are the densest bits that are hanging on, as if you stuck your finger in sand on the beach and the little bits cling to it while the wind blows it away. So in these clouds, as they get blunted, are forming little dense areas which will eventually become young stars. And you really can't see much evidence of it from the Hubble point of view because this is visible light. And visible light attenuates dust. It's the same reason your headlights bounce off a fog in the darkness. So you're seeing mostly shadow here rather than actual light. The pillars are obstructing your view. The cloud itself is full of stuff that's obstructing your view. Although it looks like there are a lot of stars here, these are mostly in front, or when really red, then they're being reddened by the cloud. But you can see hints of things happening. So let's see what happens in a little bit if we turn the James Webb Space Telescope on this. So let's go to the next slide for a moment here. I should say this is about 6,000 light years away. It's a bit farther than Orion. So Webb was launched, and I just want to draw your attention to one of the early articles on what will Webb do. The observatory will detect light from the first generation of galaxies that formed in the early universe after the Big Bang and study the atmospheres of nearby exoplanets for possible signs of habitability. So it's going to look at distant galaxies again. Oh, and maybe exoplanets, now that we've got that. That's in the public consciousness. So it's a galaxy and exoplanet machine. Well, I don't do either of those. Let's see what Webb can do for us. So let's, next slide, please. So we're going to release another terrible calibration image because we've learned so much in 33 years. So here was Webb's attempt to prove that it makes beautiful pictures by showing you a giant red snowflake. What you're looking at is an incredibly bright star that they use to calibrate Webb, to understand how to align its individual mirrors. Now, if you remember, I don't know if you've seen, I probably should have mentioned this before, Webb has a big mirror. It is 21 feet across, but it is not, like Hubble, one single glass mirror, but it is 18 gold-coated beryllium hexagons that are aligned extremely precisely to each other by pointing at stars until they go into focus. So that's what they spent several months doing in early 2022. And this is the result. You get these snowflake effects because there are two things. If you point light at the telescope's mirror, well, you hit the little gaps between the 18 hexagons. It creates speckles like this. In addition, if you look at it, there's these three rods holding up the secondary mirror in front of it, these struts, that are also blocking part of the light from coming in. So you combine those patterns together and you get this snowflake effect. So anything that looks like a point star should have this snowflake, if it's bright enough, should look like a snowflake. It's not twinkling, and it's not actually with all these points, it's just the effect of the mirror not being exactly exposed and perfect, which is reality. But, of course, what drove everyone crazy is that this picture, which was just supposed to be of a couple of stars, is in fact full of galaxies. All of these red things, spiral things, streaky things, are all billions of stars in distant galaxies that just poke up no matter what you do with Webb. They're everywhere. So maybe they were right. Maybe it is a galaxy machine. Next slide, please. It is really sensitive, is what we've learned. Okay, so back to the pillars. So you've seen this picture. What happens if we move from visible light to the infrared? Visible light is light, in case anyone doesn't know, is light that our eyes can see from the rainbow. Infrared means below red, so redder than red. That is a tiny portion of all kinds of light that we can see. Infrared is arguably a larger space than visible light. There's more colors there. Our eyes can't distinguish them, but we can translate them into colors that they can. And Webb has many colors, as you'll see. And we have made, there's a real question about astrophotography when it comes to infrared. In the same sense that there's a real question about photography when it comes to digital imaging, right? What's real? What can you, does altering color balance, perspective, choice affect the scene? What is objective reality? I could get very philosophical here, but I'm not going to. The point is Webb is really good at this. And what it will do is give you an entirely different view of this region. So let's go to the next slide and unveil the Webb version. So that's different. You can still see the pillars, but the veil has been drawn away for the most part. We're penetrating through the dust to see the gazillions of stars behind and inside the cloud. And we can see into the cloud in some places. We could see little fiery red activity, which I have this laser pointer, I should use it. This kind of thing, or up there at the edges. This is the compression, right? This is where we expect stars to form. Let's go a little farther on the next slide. I think we'll show the comparison. Yes, okay. So just a direct comparison here between Hubble and Webb. Hubble is fantastic. I work for Hubble. But this is pretty good. So you can see the differences. I mean, it's just immediately apparent how the veiling goes away. But this is using what's called the NIRCam instrument, which is the near-infrared instrument on Webb. There is actually a more infrared instrument called MURI, the mid-infrared instrument, which we're going to show that image, I think, now on the next slide. Okay, yeah. So MURI, this is an entirely different perspective, right? Now, we've gotten far enough in the infrared that we're not talking about penetrating through the clouds, but we are actually seeing the dust glow itself. Imagine if you put on night vision goggles, you could see in the dark. But imagine if instead of that, you put on heat vision goggles and you could see the heat sources. You could see the dust. You could see anything that's room temperature. You could see the glowing star-forming regions, the populations of stars being born inside this cloud. It is mind-blowing, and this is what Webb was built to do. You can see the power of Webb, and you can see why when people say, is Webb a replacement for Hubble? Absolutely not. They are completely complementary in their science cases. So you need both. Webb is the sibling to Hubble, let's say, younger sibling. And the good news is it's going to be around for a long time, and hopefully they're going to overlap for many years. Next slide, please. So all of this is to say that stars are born, and they shoot jets, and they're born inside these clouds, and it makes really pretty pictures. But I want to show you one of the most intriguing and difficult to explain pictures, or actually a few of them, of the same category. And these are called jets or outflows from protostars, young stars, like our sun, but very, very, very young, launching these jets of material high speed, creating fountains of gas and dust in the galaxy, and particularly in the cloud around them. And I want to help you understand a little bit what images like this are showing you. So the basic thing you're seeing here, right, this looks like a fountain or a wave going both ways, centered on this very, very, very bright spot, which is the star that's ejecting the material. These are sort of the shock fronts where things are slamming into things. And if this sort of shape might look a little bit familiar, on the next slide I want to show you something that you're much more familiar with that might closely resemble it, the wake of a speedboat. So if you look, the speedboat has two shocks. Shock is when, the definition of a shock is something that at high speed hitting something at low speed and causing a collision because the low speed thing is not ready for it. The water here is not ready for the boat to come crashing into it. It foams up. It does all sorts of crazy stuff. Same with this medium right here. This is called the bow shock. It is the shock in the front of the boat. And then there is the reverse shock from the back of the boat. So you have both effects. You have the material being hit by the high-speed bullet, the boat, and then you have the material that was being dragged along by the boat slamming into the slower material again and creating a second shock. This you don't have to remember all this, but this is a complicated interplay of moving things and fluids and flows, and the same kind of work is at play making these kinds of structures. It's kind of amazing. But the point is there is a bullet, and that bullet is the jet that was launched from this star that is passing through this cloud of gas, lighting it up and causing it to, the equivalent of foam, heating it up to incredible temperatures. Next slide, please. All right, so what do we do now? Right. Okay, so let's talk about a few pieces of this image. I'm going to use some analogies and some other examples. This is a zoom in on the middle. And what you can see is the middle, it's a little hard to see what's going on. You can see there's these big cones out, and then there's this incredibly bright central region. And the way that I'm going to explain this to you is by cheating and showing you a different picture of a similar object that doesn't have the big bright star in the middle. So let's go to the next slide, because it just looks better. These all have a kind of repeatable shape. Okay, first of all, I could describe this image to you by saying what's in it. So let me annotate it for you. So there's this tight bullet of jet here, some shock gas around it, and we call this is hydrogen gas, essentially moving at high speeds, and then carbon monoxide gas over here on the shell on the outside. You can see sort of puffs, and then of course this material slams into things and creates these shock fronts as it passes through cloud. But let's think a little bit more about what this means as we go forward. So next slide, please. Right. Okay, so here's a beautiful example of a central region with nothing in it, with no star in it. Now, there is a star there. In fact, it's right in the dead middle. You can see little echoes of its shadow. But imagine if there was a very dark belt tightening the middle, like a cinch. That is the disk that formed the planet, that's forming the planets. What you have to imagine is that there's a star, or even two, in here, surrounded by a disk, kind of like Saturn's rings, as we saw it before, but edge on. And that is not letting any light through because it's so thick and dark, even Webb can't penetrate it, at least not at these wavelengths. So on the next slide, I think you'll see an analogy, or a cartoon version of this. Let's see. Yes. Okay. So this is maybe something like what's happening. You have a disk, you have a couple of stars orbiting in the middle, but because this disk is in the way, we can't see the stars on the inside. But the point is they're cinched up tight, and they are in probably the star and the whole planetary system is probably contained in one single pixel of the image. And yet, it creates all of this. We'll come back to that. You can see that it's not a steady flow as well. You can see that it has ripples and eddies and shocks and turbulence as it passes out. Some of which was there, and some of which is caused by the jet as it hits the material. It's a little bit difficult to disentangle the two. Next slide. What do we got? Do we have a next slide? Oh, there we go. Right. Another thing to see here is the darkness. So this dark area, and it makes it look like an hourglass, but this is still inside the cloud. There's plenty of stuff here in the dark. You just can't see it because it's not being illuminated, because the star that would light it up is blocked by the disk, which is acting like a lampshade. It lets light go this way, but not this way. So it creates this artificial shadow called a disk shadow, very thick. So it's not that there's a sharp cutoff of material here, it's that the sharp cutoff is where it's not being excited by the light. Right, next slide. Okay, back to our image. Let's look at a different region here. I think we've got a different zoom on the next one. Yeah, okay, we're going to look at this. So this is a shock front, as I was saying before. This is where the material has either emerged from the cloud. I'll look at the big one. Is punched out of the cloud completely, and then there's nothing for a while, and then maybe it hits more cloud, or maybe maybe this was an earlier ejection that is still moving out like a knot that's still sailing outward. What you got to realize is this is about 1/10 of a light year long. It's about 1 trillion miles. It's a considerable distance. And so this material is moving quite quickly, 5 minutes, okay, great, but it is not necessarily always continuous. And this is telling us that the ejection mechanism from the central star, that one pixel in the middle, is not necessarily steady. And it's telling us something about that planetary system, which is inside that one pixel in the middle. Next slide. And I just want to show you that there's a very sharp edge to the actual cloud as well. I think you can see it here. This cloud. This is like a wall. It's like the edge of the clouds where it's being illuminated from some external source. It doesn't penetrate inside, and so there's a sharp edge. It's because these things get pushed. They create these sculpted pillars, like the pillars of creation, or like ridges and mountain-looking things. It's a fascinating region. Studying these interfaces is very powerful astronomy as well. Next slide, please. So what I want to get into perspective before I go any further, this massive thing, right, is launched from a single pixel. I mentioned that a few times. So the star, about the size of our sun, maybe a few times bigger. This is about 0.1 light years. That means, but this region, this whole area, is roughly the amount of material you would need to grab to make the sun or a star like that in the middle. So when that star formed, let's say 100,000 years ago, this whole cloud was still here. It kind of fell in to make that star and its planetary system compacted in that one pixel. That would be the equivalent. So the equivalent of essentially taking and then that tiny system shot a jet this far back out or all the way. That's the equivalent of saying if you took the entire state of New York and you gravitationally pulled it into one half of a peanut, and then it packed New York's mass into the peanut, and then shot a jet back out to Albany from the peanut, from here. That's the scale and ridiculousness of this image. That is how much influence the formation of a single star like the sun has on the cloud around it and the imprint that it leaves. And if you were flying through our solar system 4.6 billion years ago, maybe you would have seen something like this. It's just astonishing to think about it. So this image is so much more than beautiful, but it is beautiful. And it has one other mystery, which I should show you on the next slide. Which maybe you've heard of or not. Well, what is it? Probably a distorted galaxy, would be my guess. It could be an escaped knot from this. It's very difficult to tell until we do a spectral analysis of this thing. But for that, we would have to get a little bit more data from Webb. So this question mark will remain a mystery for a little while. So what is Webb about? Next slide. Galaxies. It's all galaxies. So what made the cover of Time magazine? Galaxies. So I'm here to tell you that Webb is not just a galaxy machine. It also does other things, beautiful things. And this is something we're going to appreciate for a very long time. And maybe in these galaxies, maybe elsewhere, is that new physics, that new field of study that Webb might uncover that has not previously existed. And I'm going to leave you with one last thing, which is that I also do like black holes, like our next speaker. And I wrote a book on black holes aimed for middle schoolers. Next slide, please. So please feel free to enjoy. It is a fun read about the history of black holes, what they are, and I promise that people older than 12 can also read it. So enjoy. So thank you very much for your time and attention, and I think I'll leave it there.
Thank you so much, Dr. Green. Wonderful job there, and a wonderful explanation of that special image there.